Alright, in this video we want to review sequences, converging or diverging, and then we want to extend our work with L'Hopital's rule. So, does the series converge or diverge? Let's start with that. This first one, remember, we're always just thinking if I took the limit as n goes to infinity, I'm just going to make a little note here, if I did the limit as n goes to infinity of whatever my sequence is, do I get a number? If I do, it converges. So this first one, if this gets bigger and bigger and bigger, the limit becomes 0. So it does converge, and it converges to 0. Okay, next, this one, if I took the limit as n goes to infinity, it would converge. It would converge to 1/4. Finally, next, n squared plus 3n over n minus 4. The limit there would be infinity, so this would diverge. And finally, n over n factorial. I hope you think about this and you say, boy, if we're going to infinity, this gets big, but this gets really big. I hope you have a sense that it would converge towards 0. But I wanted you to think about a little algebra here. So n factorial, remember, I'm going to put n on top, is n multiplied by n minus 1, multiplied by n minus 2, multiplied by n minus 3, multiplied by on and on and on, all the way down to 1. So the algebra here, the n's will cancel out. No matter how big it is, n will cancel, and we'll be left with 1 over n minus 1 times n minus 2. So obviously the bottom will still be large and the top's just 1. So this definitely converges to 0. Now, I wanted to remind you of the L'Hopital's rule forms we've already seen. Again, we plug in 3, we get 0 over 0. This is the first kind of indeterminate form. Okay, 0 over 0. I'm just going to make a note. This is when we've used L'Hopital in the past. And our kind of shortcut way here of handling this now is we said, okay, well, what's the derivative of the top? 1. What's the derivative of the bottom? 2x. Now we plug in 3 again, and we get 1/6. Okay. The next one, if I plug in infinity, I get infinity on the top, and I get infinity on the bottom. This is the other type of L'Hopital's indeterminate form we've talked about. And we said, well, we could certainly just use our asymptote rules. That'd be easy enough, actually. 2 over -6 would be -1/3. Or we could do L'Hopital. So 4x on top, 3 minus 12x on the bottom. If you plug in infinity, you get infinity over infinity again. So we do it again. We do 4. Derivative's -12. So 4 over -12, which we said was -1/3. Okay. So L'Hopital's rule works there as well. So these are the forms we've talked about with L'Hopital's rule. Now, what this is actually what's called the strong form of L'Hopital, because this is what we're going to take every other indeterminate form and aim for. So when I say weak form up here, I mean this is how we're going to, these forms that we've already used, this is how we're going to use those to do harder problems. So for example, here are 2 more indeterminate forms. 0 multiplied by infinity, and infinity minus infinity. So this first one, if as I go to infinity, x gets larger and larger, the sign, well, 1 over something big gets close to 0, the sign of 0 is 0. So it is infinity multiplied by 0. Okay. Here's how we handle it. We rewrite it as the sign of 1 over x divided by 1 over x. I'm going to write the limit statement in there again. And I want you to just think about this. If I divide by 1 over x, that's the same as multiplying by x over 1. So I haven't changed anything. Well, now, if you think about L'Hopital's rule, you say, well, if I plug in infinity, I get 0 over 0. Now it's the old kind of L'Hopital. So as I said, we use our strong form 0 over 0 and infinity over infinity to deal with all the other forms. So I do the derivative, negative 1 over x squared, and I do the derivative up here, which would be the cosine of 1 over x multiplied by negative 1 over x squared, right? Because of chain rule. So now you'll notice those negative 1 over x squareds will cancel, and all I've got left is the cosine of 1 over x. And if I plug in infinity to that, if I do the limit as x approaches infinity of the cosine of 1 over x, well, the cosine of 0 is 1. Okay, so let me just recap that real quick. We just did some little algebra. We said, you know what, this comes out to be this form, infinity times 0. I took the x and I dropped it in the denominator as a 1 over x. That didn't change anything algebraically because dividing by 1 over x is the same as multiplying by x over 1. Then I had a form of L'Hopital I was used to. So I did the derivative of the top with chain rule, derivative of the bottom. The two terms canceled out and I was left with this. And of course, once things start working with L'Hopital, you try and plug in again. Plugging in infinity, this is 0, so the cosine of 0 is 1. Okay, next form, infinity minus infinity. Well, if you think about this, you know, we got 1 over 0, which is an asymptote, minus 1 over 0, which is an asymptote. So the way to handle this, maybe you already have some kind of inkling, is again to use some algebra to think about a common denominator. Okay, so I'm going to, over here I'm going to write natural log of x multiplied by x minus 1. And on the top I'm going to have x minus 1 minus the natural log of x. Now what we should just see here is that, you know, we haven't changed anything, we just got a common denominator, and if I plug in 1, so 1 minus 1, 0, minus natural log of 1 is 0. So top is 0. Natural log of excuse me, this should be 1 right here. Natural log of 1 is 0, 1 minus 1. So I have 0 over 0. So what I've got here is a form for L'Hopital's rule, right? I have 0 over 0. So I do the derivative of the top, so 1 minus 1 over x, and I do the derivative of the bottom, which I'm going to need product rule for first. Let's do it in the right order. First times the derivative of the second plus the second times derivative of the first. Okay. Well, now if I plug in 1, I get 0 on top and I get 0 on the bottom. But that just means I can use L'Hopital's rule again. Okay, so let me kind of drop it down here if I can. Let me do the derivative. So derivative of 1 minus 1 over x is negative 1 over x squared. Derivative of natural log x times 1 is 1 over x. And derivative of x minus 1 is 1. We're still doing the limit as x approaches 1. So now I plug in 1, I get negative 1 over 1 squared. And I get 1 plus 1, which is 2. There's the limit. So it took L'Hopital's rule twice, but I was able to do it. Again, infinity minus infinity, we got the common denominator, and that gave us a L'Hopital's rule. Now, this is not magic, and these problems are not, not hand-waving. The reason these are indeterminate forms that work with L'Hopital's rule is because algebraically we can manipulate them into 0 over 0 or infinity over infinity so they match what we had before. Okay, this is not fancy. I mean, this is just us being able to do some algebra and manipulate it into 0 over 0 for both of these. And this is almost always the case with this kind of problem where you just drop the infinite one in the bottom as a reciprocal. this form, we almost always are going to just get a common denominator. Now, the last three indeterminate forms, you'll notice, look very similar to each other in that they are all exponentials. And the nice thing is we're going to solve them all the exact same way. We have, 1 to the infinity, 0 to the 0, and infinity to the 0. And again, the whole point of this is that we are going to manipulate with some algebra these back into problems we've already done. Okay, so let me show you this first one. I'm going to just kind of up top here, I'm going to write that y is equal to 1 plus 1 over x to the x. I'm going to take the log of both sides. Remember, log drops the thing out front. Okay, now I'm going to take the limit of both sides, and I'm going to kind of ignore this for a minute, but just remember it, okay? So now I want you to think about plugging in infinity, okay? This would get large, infinity, 1 plus 0, so the natural log of 1 is 0, infinity times 0. This is one of those forms we saw in the previous slide. So I'm going to drop this down to be 1 over x, like that. Dividing by 1 over x is the same as multiplying by x over 1. And now we can do L'Hopital's rule because these come out to be 0 divided by 0. So the derivative of the top is 1 over 1 plus 1 over x multiplied by negative 1 over x squared with chain rule. And the derivative of the bottom is negative 1 over x squared. So these cancel out. We plug in infinity and we get 1. Now, this unfortunately is not the limit, okay? Because you got to remember we had taken the natural log at the beginning in order to manipulate this algebraically. So now we have to go back and we have to say, well, we really have the limit of natural log of y. How do we get rid of natural log? We take e to both sides. So e to the first is the limit, or just e. Okay? So the limit is e. Now, I know that there's a lot that went in there, and it went in there really quickly. I'm hoping, because I'm going to do the others, I'm hoping that they make sense because they all are very similar. Okay, so again, let's start by just rewriting this. We say, okay, y is equal to x to the x. So the natural log of y is equal to x natural log x. Okay, if I plug in 0 to this, I get 0 times infinity. So we're going to use L'Hopital's rule again. We're going to have natural log of x over 1 over x, like that. Okay. Okay, L'Hopital, 1 over x, negative 1 over x squared is the bottom. Now this doesn't seem to help us, but I want you to think about this. If we can do 1 over x and multiply by the reciprocal, negative x squared over 1, that's just negative x. And the limit at 0, remember we're taking the limit at 0. Well, plugging in 0 then, the limit as x approaches 0 of negative x is 0. But remember, we had to take the natural log. Okay, we had to take the natural log, so at the end we're going to have to do e, so e to the 0 is 1. So that is our limit. Okay. Let's do one more like this. Okay, so y is equal to x to the 1 over x. So the natural log of y is equal to 1 over x, natural log of x. Okay, again, as we're going to infinity, we end up with 0 times infinity. That's definitely a form. So then we could rewrite this as natural log of x over x to the limit as x approaches infinity. Use L'Hopital's rule, 1 over x over 1. As we go to infinity, this is 0. And remember, again, because we took the natural log, to get back to the end we have to do e. E to the 0 is 1. So, lots of different things happening here. And these are the 5 new indeterminate forms. Again, L'Hopital's rule has a lot more power. The AP exam doesn't necessarily test all of these, but they're really helpful as you do sequences and series to know these other indeterminate forms. And they are all just manipulating, with some algebra, these new forms into problems we already have worked.